building the road, and then... So in northern Oman, there's a big block of oceanic crust and upper mantle that's been thrust onto the Arabian continental platform. And then it was subaerially exposed, it was eroded and tilted, and now you can walk down these beautiful canyons and you can basically descend 20 kilometers into the Earth's interior.
But that would also help to explain their kind of sheet-like geometry.
Line up here somewhere where we pulled out a bunch of it. What we're looking at here is a piece of the Earth's mantle that has taken up CO2 so that every single magnesium atom in these rocks has made friends with the carbon dioxide to form solid limestone. When the Arabian continental platform was subducting because you have stress building up that cracks the rock. And they've taken up about 1 billion tons of carbon dioxide. This mountain up to our east is entirely composed of this magnesium carbonate plus quartz rock, and there's about 1 billion tons of CO2 in this mountain.
From 0 to we start 3 meter, then 3, then 3. In that way, particular way, we'll reach now 377 meter. So it is almost, it has taken 20 to 22 days almost. And now, hopefully today or tomorrow, we'll finish 400 meter.
Today we have, as of now, we have completed 393 meters.
While the core is here, each piece which is broken one from the drilling, so we do a sort of jigsaw puzzle, and we mark, with the red pen, we have mark on both of the pieces. So whenever these pieces are separated, we can fix them again.
Roll the image. We can use these images to try to help us figure out the different generations of mineralization and therefore piece together at what different periods in geological history and modern history carbonation is occurring.
Describe all these white, all these Peter interacted with fluids. You see this sort of greenish stuff that.
And we don't get to see much. You go down in a submersible and there's a little flashlight basically. The Earth's upper mantle is very far from equilibrium with the ocean and the atmosphere. And so when the mantle does come to the surface, this large chemical disequilibrium is like a battery. It's like a big store of chemical potential energy that drives these very rapid reactions of carbonation, hydration, oxidation. What we have in mind is to study the natural process and understand it as well as we can, and then to try and design engineered systems that emulate the natural process as closely as possible. So we have to do the least amount of input of other energy, take maximum advantage of the chemical potential energy that's just inherent in having these rocks near the surface. And that should yield a process that costs the least in terms of energy, in terms of money, for taking CO2 directly out of air and surface water.